Yeah, we are live.
So we can start. It's 5:30. The room is open, right?
Yeah. They're good to go. We are streaming right now.
Okay, I can't hear anything if somebody was saying.
Yeah, we are good to go. We are streaming right
Okay, I think last moment issues. Yeah. Quick audio check. Siddharth, if you can speak something.
I can hear you.
Awesome. I can also hear now. So we'll wait another 3 to 5 minutes for people to trickle in.
Yeah, sounds good. Should we kick it off, Amir?
Sure, let's do it. As we have quite a lot to cover as well, right?
Yeah.
So, hello everyone, and welcome to the fifth elephant paper discussion on latent diffusion, more popularly known by its implementation on as stable diffusion. Right. My name is Amir, and I'll be the moderator for today's session. Quick intro about me. I've worked at ThoughtWorks and Gojek. Right now, bootstrapping my own generative AI startup. Earlier this year, I launched a stable diffusion based fantasy profile pic generator, and later on also shared my learnings on stable diffusion via Udemy course. That is how I know Siddharth. We interacted when I was actually working on this course. So thanks, Siddharth. And over to the presenter, quick intro about him. Sid works at RTL Germany. He's responsible for multiple teams working on streaming platform RTL Plus. The data product teams at RTL are working on enriching the metadata of the content catalog and also using GenAI techniques for multiple use cases like digital product placement in ads. On his own time, he loves to teach, also offers a free course in collaboration with OpenAI on using prompts to build products. The fifth elephant paper session is curated by Bharat Shetty Barkur, along with the GenAI community experts. Bharat has worked with Atel Labs, Symphony AI, and various startups in IoT, healthcare, and genomics domain. He currently consults on AI, ML, and backend engineering. Most recent project includes building and scaling chatbot platform for Atel customers using a host of technologies like SCT, TTS, and NLU. The aim of the paper discussion session is to foster community dedicated to demystifying research papers through practical code-centric discussion methods. The session will be held once every month, either online or offline. So that's about the intro. Let's jump on to the topic for today. So why stable diffusion? There has been an explosion of interest in the image generation space because of the image generation models like DALI, Midjourney, and later on Stable Diffusion. With the DALI and Midjourney, they are closed source. But with Stable Diffusion, it is open source. And because of the open source nature, it has led to a huge online community that is actively exploring various customization techniques and building mind-blowing applications. Today, we are here to understand the techniques and model behind this technology by diving deeper into the paper that actually drives it all, the latent diffusion models. A quick thing about the Q&A moderation. We'll have a quick time check set 20 minutes and 40 minutes into the session where we can take the relevant questions. We will definitely have a Q&A session at the end of the complete presentation. You can post your questions on the Zoom chat. I'll either try to answer it myself if there is something we have covered during the session, or queue it up for Q&A whenever we take it up. Do also check if the question has already been asked so that it basically helps me speed up moderation. Also, we encourage women and a person of other gender participation and people with disabilities to ask questions. At any point of time, DM me on the Zoom chat if you have any suggestions or comments. We have a lot to cover, so without further ado, let's kick off the session. Over to you, Sid.
Cool. Yeah, thanks a lot, Amir. And yeah, glad that you could join us today as well. Certainly, I'm not the expert on these topics, but I've kind of dived into them along with Amir and so on. So I think what we are trying to aim for here is a healthy discussion today on, yeah, what stable diffusion is, what the latent diffusion model says, and kind of dive deeper to understand how it really works. Nothing here is super original. I've put together different kinds of sources and I have linked them where it's applicable to kind of give you more information if you want to read further and stuff like that. So hopefully you will find the session interesting. I also wanted to thank Hasgeek and the Fifth Elephant community to kind of give us the platform and the space to have these paper discussions. There are more planned. I think Bharat will talk a bit, or maybe can give information in the chat about it at the end. The next paper, I think, is the Transformers legendary paper. But yeah. Let's get started. So what I wanted to also quickly show you in this intro slide itself is, of course, diffusion. So why is like diffusion is a process through which the atoms disperse through the space. That's what you see in this visualization over here. It's, of course, a thermodynamics physics concept, and that has kind of been borrowed and applied in the space of image generation. I also wanted to show you another example of diffusion, not really diffusion, but kind of traversal in the latent space. That's what you see with my photo. I just put my photo into an app, and then it tries to find similar representations of that photo and then kind of navigate in that latent space. So just wanted to use that as a motivator to say, hey, we're going to talk about latent models and we're talking about diffusion. So that kind of comes together in this whole space. But yeah, that's the topic for today. But before that, just a very, very brief history of image synthesis. So Stable Diffusion is not the first model that is able to generate images and so on. And there's really been a long progress over time. And that's what you see in this picture, where starting in 2014, you had really small images. And by small, I mean the number of pixels. So every image is horizontal by vertical, and each of that is a pixel. Typically, a high resolution image would be 1024 by 1024 pixels. So that's basically what you would use. And you can see how over the years, of course, the resolution of the pictures that has been produced has improved. But at the same time, the quality of the pictures that has been generated has also improved. So There are several models that did it, starting from autoencoders to something called as generative adversarial networks or GANs, to now where stable diffusion is sort of the state of the art or one of the most commonly used techniques to do image generation. So, but before that, there is a lot that comes, and a lot of that is sort of reused or repackaged in the stable diffusion paper. So it's not like, boom, stable diffusion just came out of nowhere. It kind of reuses a lot of the components, and that's kind of what we're going to dive into as well. Of course, the application of image generation is just immense. It's of course used in e-commerce to generate product images. It's used in movies to come up with different ideas, skills, and stuff like this. And of course, visual effects, VR, AR, and stuff like that. So the applications are really limitless, some of which we also use at work. But yeah, that's just to give you an overview. But before we jump into the stable diffusion itself, I just wanted to sort of go into this latent space, or what do we mean by latent diffusion, right? So the entire, the name of the paper itself is actually Latent Diffusion Models, which then later became Stable Diffusion, V1.4, 1.5, and then there are the most recent version of it is Stable Diffusion XL. So that's kind of the model that's popularly known as, but the paper itself was called Latent Diffusion Models because it combines basically two important things: the latent space representation and then diffusion in that latent space. So the first thing there is the latent space representation itself, and that uses an existing model, which is an autoencoder. Again, an autoencoder is nothing new. The first autoencoder was already available in 2012, and that's also not just restricted to the image space. It's used across text and several other modalities. So what is the autoencoder? The autoencoder is a neural network. It is a type of model that basically tries to create a very, very finite and constricted representation of an actual object. So what you see in this image here is that you have a hand-drawn digit. So it's actually an image of the number 4, which is passed into the encoder, which is, you can imagine it to be a neural network. And then there is a middle layer, which is called the latent feature or the latent representation. When you have this input image, let's say it's of the order of 1024 by 1024 pixels, you would then try to have a latent representation. So it's simply a vector, and this vector will be of the size, let's say 512 or 256. So something really, really small as compared to the original input image. So the input image is 1024 by 1024. So you have a pixel in each of those 1024 by 1024 grid, and each pixel is represented by a RGB value, a red, green, blue value. So you actually have a very, very detailed information about each and every pixel and the kind of color that it contains, and that's how you store an image. But that's still quite complex and large to deal with when you're talking about matrix multiplication. So then you use an encoder to bring it down into a very, very small 256 or 512 vector representation. That's called the latent feature. And then you use a decoder to kind of reconstruct that image again. So what this is doing is it's going to look at that latent representation and try to recreate the same image as it had in the input, right? So you have an input, you try and pass it through the encoder network, you create a very small representation, then you have a decoder network that tries to recreate the same image from this latent representation, and you know how the original representation should look like, and so you can subtract the two, see how far away you are, and sort of train the image, train the model. So the goal here is to get to a latent feature representation that is so good that the decoder can almost completely recreate the image from just this representation, right? So you train over multiple images and over multiple epochs to arrive at a model that is very good at encoding itself. So given an image, it encodes it in this latent space and then is able to recreate. But now, the first thought that comes to my mind is, well, why? How does that make sense? Because you already have the image. Why do you want to create it again? The reason being is that this latent representation is actually the useful part. So what you have actually achieved here is a sort of compression technique. So you have been able to take an image that's 1024 by 1024 or whatever the actual number of pixels and create a very, very small representation of it, which throws away all the unnecessary information that is there. And we are also able to create the image itself from this latent representation. That's why the decoder is there. But now you have a very, very small representation with which you can work with, which is much easier to work with as compared to working with the actual image itself. So that's the reason why these autoencoders are so useful. On its own, it probably does not have too much value. You can use it for denoising and stuff like this, but its real application comes when it's used in that latent space or the latent space that it gives you, and where you can use that. That's really where the autoencoders shine. And that's also how they are used in Stable Diffusion. So just wanted to say that I briefly wanted to introduce the autoencoders as a concept, as they are used and are important component of the latent diffusion models, which we will see in the next slide. So the approach that I'm going to take today is, first of all, just look at a high-level diagram overview or system architecture, however you want to think about it. This is just the way I explain it to myself. So kind of in the form of boxes, kind of understand the process that's happening. That's what I will focus the next few minutes on. And after that, we would try to go into the code where we try and look at each of these box structures that we have seen and how that translates into code. So like a two-step process. In the first step, we will look at this system architecture view, kind of understand how it really works. And then in the second step, look at the code and relate each of those code steps to each of these components. So that's sort of the approach that I plan to take today. But okay, now we come to latent diffusion models. This is, of course, the image itself is also adapted from Jay Alamar's really good article. So I've also linked it here. Feel free to go through it. It's quite detailed and really very well explained. So definitely inspired from there, I've made my adaptations. But I'm going to cover, or at least what I'm trying to do is cover each of these boxes in their individual parts first. And I would also use a whiteboard to sort of explain and kind of walk through the entire process as a way to sort of explain the whole thing. The main three components on the left, you have the text encoder. So it's actually the vision text transformer model. In the original paper, they actually make use of a different one, but Stable Diffusion v1.4 uses the clip model. This is a clip model that has been produced by OpenAI and is also available open source. That's the left-hand side. Then in the middle, you have the UNet plus the scheduler. This is where the actual diffusion process takes place, which is kind of the heart of the entire model. And then on the right, you have the image decoder, which is basically the decoder part of the autoencoder, the one that we saw in the previous slide. And that's used to kind of generate the final image after the diffusion process has been carried out. So those are the three large blocks, or some way of thinking about it. What I would do now is sort of jump into a bit of a screen sharing model. I think this should work. Yeah. Cool. So you should be able to see the same slide. So I basically, just copied the same slide. But what I'm trying to do now is basically go in a bit deeper into each of those and kind of talk about how it really works. So let's start with the one in the middle first. So the UNet and the diffusion model itself. So what happens in the diffusion model, right? So at the first step, you have training. And in order to train such a model, what they do is actually add noise to existing set of images. So let's suppose that you have an image. You have an image that looks like this. Let's say it's an image of me, that, the kind of the one that I showed on the first slide. So that's an actual image. I kind of, look this way. And I progressively add noise to this image in steps. So for example, as just the step first, I can take this and I have still my existing image, and then I add a bit of noise to it. right? So there is a certain distribution in which this noise is added and so on, but I'm keeping it still at a high level. So you add a bit of noise to this image. So it still looks like me, and you can make out there is a human face, but maybe it's not so clear. And then I do another step and add even more noise. So it's still an image of me, but then there is a lot more noise now around this. So a bit harder to read, and so on. So imagine now you can repeat this process for a certain number of steps, as they are called. So let's say, at the end, what you would end up with, so this is obviously a bit more noise than others. And then finally, at the end, you will end up with completely random noise, right? So you have just noise in your final image because you have progressively kept adding noise and noise and noise and so on. And you have done this now over several steps. So let's say this could be called step 1, this could be called step 2, this could be called step 3, and, right? So you basically have an image, and then you have multiple versions of that image with a certain degree of noise, with a certain distribution that are added to it. That's basically what you have achieved. This is also called as the forward diffusion process. So it's a process by which you are adding noise and diffusing that through the entire process. Now, what do you do in the reverse process? That's actually now when you start to train the model, right? So you have, so what is the model? So the model is actually a U-Net model. It's called a U-Net because it is in the shape of a U, and literally it looks like this. So something like this. It is also an autoencoder model, so very similar to the one that we saw in the first slide. It is exactly the same sort of model. So it is an autoencoder. It takes in an input image, it has an output image, and these are a set of encoder components. These are a set of decoder components. So very, very similar architecture with some differences, for example, which is why it is actually kind of shaped in this U form, which is because they have these cross attention layers which link certain parts of the encoder to certain parts of the decoder, right? So this is again, so the U-Net itself is not a new model. It was already introduced in an earlier paper somewhere around 2019. It is basically an evolution of the autoencoder architecture with cross attention, basically. And that's the U-Net paper, so U-Net model. And this model is the backbone of the diffusion process. So you would use this model in order to now input these images. So let's say you have these set of images that you have now created, where you have added pieces of noise to that. And at each observation, so one observation to this U-Net model is going to be, for example, let's take this image, the one over here, and it is basically at time step n equal to 1, and you have my face, and you have a bit of noise, not a lot of noise. And you input both of these to the U-Net model, and you ask the U-Net model to come back to the original image. So you want to actually say, hey, can you please denoise this image and give me the original one? And that's the goal of the U-Net. Again, here, you know what the original image looks like because you have it here. You can compare the output from the U-Net, compare it to the original image, and you know how much is, how close they are. You have the error metric, and then you can sort of train it in this fashion. Except now, you can obviously train it across all these images, across all these time steps, right? So you can, of course, in another iteration, pass in a much more noisy image. So you could say here, this one, and this is, let's say, from time step n is equal to 3. You put both of these into the model, and you ask it to predict the original image, right? So you can say, hey, please predict the original image to me. Now, obviously, this one, so going from n is equal to 3 to n is equal to 0, is a bit harder because you have to predict a lot more of the noise as compared to going from n is equal to 1 to n is equal to 0, right? So there is also what exactly the model is trying to learn is a bit harder at each step because there are different amounts of noise that are available at different time steps. And that's the reason why into this diffusion model, you also pass in the timestamp to the unit. So when you're training this unit now, you pass in the image, the noisy image, and you also pass in the timestamp, both of which help the model to understand how much noise should I remove in order to get back to the original image, right? So that's basically what is the role of the unit, or how the unit is trained. And now, of course, you have a large data set of images. So we're talking of the order of 3 billion images that was part of the LION data set that is used to actually train this unit. So when you train this, and as you train this over multiple epochs and so on, you are basically training the unit to get really good at denoising images. So that means that you give it any noisy image or even just random noise, it is able to denoise it and give you back the original image. So that's basically the goal of training the unit. And that's what the training process ends up learning. But now you might actually say, okay, but where does this whole text part comes in, right? Because so far what we have seen is only that, hey, there is an image, and then you take an image, and then you denoise it, and then you get a new image. But how does this whole text generation process itself happen? So that's actually very interesting, and maybe that's something we can kind of change into the training period and the inference time distinction. So far what we saw was, how do you actually train this unit? By showing it multiple images, noise at multiple timestamp, provide in the noisy image, provide in the timestamp, and then the model learns how to denoise something. But what we have not done is conditioning this. So that means that when you have an image, you don't want just any random image to come up. You want an image that corresponds very closely with the text input that you have given, right? So you need to be able to say, hey, I actually want an image of a pig, or an image of a dog, or an image of an apple. You want to be able to say this and actually synthesize this image and not just any random image. So what happens at inference time is that you actually start with completely random noise. So this is also just the last stage over here, right? So in the training process, we said you keep adding noise, goes up till the end, and at the end you have a fully noisy image over here. This is the starting point for our inference time. So by inference time, I mean when you're actually generating the image. So the starting point is always the complete noise that you have. And then you pass it through the unit. So you have this unit, and what does the unit do? The unit has already been trained to denoise an image, and it will give you a denoised image, which will be, let's say there is, let's assume we are still talking about my face. You will have some form of, yeah, my face or something like this, and also noise, because yeah, that's how it works. It doesn't work extremely well at removing all the noise, but it actually removes some of the noise. And then what you would do is take this back into a next step and put in this slightly less noisy image into another run of the unit. And then you get back a slightly less or more clearer picture of me with a slightly less noise. So at inference time, what happens is you start with a completely noisy image. I mean, it's not even an image, it's just noise. You pass it through the unit. The unit is great at reducing noise. It reduces the noise, but it's not able to reduce the noise completely because it has also learned to reduce this in steps. And so it doesn't reduce the noise completely. It still produces an image with a bit of noise in there. So for example, still maybe an outline comes out. And then there is this, which you run through another iteration, where it tries to reduce the noise further and then produces a less noisy image, and so on. So this is something that you typically would do 50 times, which is what we will see in the code. You can do it lesser, you can do it more, but we will talk about that a bit later. But this is what happens in inference times, where you start with random noise and you want to come to a final image, and you do this by multiple times running through the unit. Now, come back to the original question, how does the unit know that it needs to produce the image of me or a dog or an apple or whatever, right? Right now, we haven't really provided it any input in that way. And this is where the conditioning comes in. So actually, when, let me maybe remove this piece of stuff just to make it a bit easier. And I will represent it in a bit of a different way. Sorry. Okay, so you put in, you start with the noise, so full noise. You pass it to the unit, and you will get a slightly less noisy image. But at this point, what you also additionally put in is the prompt. So this is the prompt that you have given to the image, which is nothing but a photo of Siddharth or a photo of an apple or whatever your prompt is. And what this we do now is you actually take the prompt and then you embed it using the clip embedder. So if I go back here, this model, the OpenAI clip model, is now what we call as a vision text transformer, which tries to embed, so it has already been trained. It is available as a pre-trained model, and it was trained using a bunch of images and their captions. So, and the way it was trained is that it would create an embedding. So this is an embedding where you have images over here, and you have text, their corresponding text captions over here, and any image over here would be kind of one point in this embedding space will refer to both the text and the image. So this model is trained in such a way so as to maximize the text image embedding, so that when you pick a particular point, it refers to one image and it refers to the caption of that image, and it tries to keep the text and the images that are not related to each other as far apart as possible. So that's the training objective of the clip model. Again, not going into too much detail there because that's yet another model of its own, but the goal of the clip model is to basically provide a joint embedding space where you have vision concepts and text concepts together in an embedding space. And that's really the key role that the clip model plays in Stable Diffusion, because now when you have a prompt, a text prompt, what you do is you take that text prompt and you embed it in this clip space. So you take the text prompt, a photo of Siddharth or a photo of Apple and so on, and you embed it in this clip space, and what you get out of it is an embedding vector. And this embedding vector is what is given, so the prompt, which is in the form of text, so here, which is then embedded. So this is the embedding. And this is given as additional input to the unit. So this is the conditioning step of the unit, where when you are going to denoise an image, so you start with fully random noise, but you want to now denoise it, but you want to denoise it in the direction of this prompt. And the way to do that is by embedding the text prompt in the OpenAI clip embedding and retrieve that and provide that as input. So when the denoising process actually happens, the image that is generated or the direction in which the image is denoised is defined by the clip embedding. This is, of course, not happening only at inference time, but also at training time. So when you are training the unit model, at each of these time steps, when you are denoising it, the additional input that you give here is the OpenAI clip embedding. So this is the reason why the unit model knows that I need to reduce noise. I need to reduce noise based on the time step. And I need to reduce noise in this particular direction, which is the same caption for that image. So during the training itself, you are going to give it the, the noisy image, you're going to give it the timestamp, and you're going to give it the clip embed. So this is the conditioning step, basically, that takes care of the fact that you start with random noise, keep reducing the noise in steps, but in each step, you are removing noise in a certain condition or in a certain direction, which is provided by the clip embedding. So that's basically what is happening in this whole inference time. So you basically have this. So now at inference time, what happens is you start with a noisy image, you have a prompt, you then embed that prompt, and then you give it into the unit model itself. What you get back is now an image. Let's say you want an image of an apple. I'm really bad at drawing, but you get a faint outline of an apple. Let's say this was apple. And you have embedded it, you have given it, and you get a faint outline of an apple, and there is still a lot of noise. And this now you provide to the next iteration of the unit, and along with the same embedding, and then you get a slightly less noisy image of an apple with a little bit noise, and so on, and so on and so forth. So this basically process is repeated roughly 50 times as an indicator for the denoising process to happen. So that's what exactly we will see now. I just saw a question, does the text prompt remain the same through all the steps? Yes, the text prompt remains the same through all the steps. That's also how the model was trained at the training time. Cool. One thing I forgot to mention now in this whole space is, so far we were always talking about the image, right? So we were always talking about the fact that, hey, here is an image of me, and then you're adding noise to it, and so on. In reality, that is not what is happening. I use that as a way to explain the process, but in reality, you don't use the image itself, but you use the latent representation of the image. So that means that you actually operate in the latent space. That is basically why I introduced the encoder. So imagine exactly the same process happening, but on this latent vector, on this super precise representation, which is much, much smaller and easier to work with than the actual full image. So you still add the noise, you still add it in stages and so on. Everything remains the same, but you don't operate on an actual image itself, but you operate on the latent representation of that image, which is given by the variational autoencoder. So that's the kind of reason why this paper was cool, because so far the diffusion process was always happening in the image space itself, which is quite massive and takes a lot of time. It's highly memory intensive. And then what this paper did was introduce the variational autoencoder. Then you condense it down into the latent space. And then in this latent space, you add noise and do all these things and stuff like that. There are a couple of other changes. So in the actual process, I will maybe go through it when we go to the code, but I just thought maybe it's a good time to also take a pause to see if there are any questions before we dive into the code directly, or look at the small modifications.
Yeah, there is just one question from Chaitanya. Does the text prompt remain same through all steps?
Yeah, that's kind of what I answered as well. I think it remains the same throughout the whole process, both during the training time and during the inference time. You give it just one. We will see it actually in the code. You just give it one, and then go in different direction. There is a bit of a nuance there, but I will cover that when we come to the code.
Yep. So Maheshwaran asks, how does a clip embedding direct the generation of image?
Yeah, exactly. So this is actually a very good question, because I didn't actually look at it in detail when we were doing this here. So during the training process, right, you have the actual original image. So you know what, let's say it's a photo of an apple, right? So you have, what do you have? You have the image, which is the photo of the apple. You have a caption for that, which likely says photo of an apple. That's the prompt in the training data set, or the caption. And then you have multiple noisy versions of that particular image. Now, when you're training the unit, you give 3 inputs to the unit, which is the noisy image, that's the first one. Then you give it the time step, that is the second one. And you give it the embedding clip of the caption. So a photo of an image, embed it into the clip model, retrieve that and pass that. So now at the end, you are trying to generate the same photo of the apple, right? So you are going to compare the output of the unit with the output of or with the original image. And that's basically also the next question, which is how are image generation models evaluated? That's basically your error metric. That's kind of what you are training on, and you want to reduce this as much as possible. So that's during training time. Now, while this training is happening, what you are doing is you're sort of generating the image or denoising the image in order that it takes into consideration the original image, because that's what the error metric does. And because the embedding from the clip model is also an input to your denoising process, it is also the parameter based on which you're adjusting it. So when you have an image of an apple versus you have an image of a monkey, the clip embedding for both of these are different. So as the model learns, the model also tunes itself to denoise this particular one in the direction of an apple. And how do you verify that? Because it has to generate an apple, that's the error metric. And then the other one should generate it more in the direction of a monkey, because again, the same error metric applies. So you're basically using the clip embedding as the directional mechanism for how the denoising process happens. So when you have an image of an apple, the caption of an apple, then the model sort of learns that, hey, this is the embedding and I should generate it in this way. And it's a different embedding for monkey because they're completely different. And here I should do it in this different way. So that's kind of how it directs. And maybe I can also take the second question already, how image generation models are evaluated. This is a very good question. Typically, there is the error metric. That's kind of what you would use. I don't, off the top of my head, I don't remember which is the one specifically used in the Stable Diffusion paper itself, but that's during training time. The way things are evaluated at inference time is a bit more human evaluation based. And there is another metric, which, yeah, I also don't remember right now. So maybe I can come back to that or we can look into the paper. But yeah, maybe I move on, and then we can come back to Akash's question, just so we have time to go through the code before the hour is up. We can also take the Q&A at the end, so I think that's not a problem. I should have set this up already. By the way, this is a good point as well. I'll just post this link. It's a link to where the presentation as well as this notebook is available. It's just a Google Drive, a shared Google Drive. So feel free to look it up, and yeah, you will have the slides, you will have the notebook as well. Let me stop the share here and then share my screen again. Okay, you should be able to see the notebook. Yeah, so like I was saying, I posted the link. This link is to a Google Drive, which has both the presentation, yeah, it's just a few slides, and then also the notebook. So you can, yeah, try both. I am connected. Yeah, I think for those of you who are not familiar, there are just, I don't know why it got disconnected, but there are just some libraries that you install at the beginning. So these are, I'm using everything from the Hugging Face library. So nothing, again, super different here, and I'll show you. So now what I'm trying to do is go through the code, and in the code, draw parallels to this block diagram that we kind of looked at. So yeah, I'm going to use the repo of the Stable Diffusion v1.4, which is hosted on Hugging Face. You just need to create a Hugging Face account if you don't have already, and then copy paste your token into that. You need this because all these models are hosted on Hugging Face and also their repositories. So you can kind of do that. This is set up in a Google Colab notebook. You can pick to have a GPU. It should be there by default. The T4 GPU is available even in a free account, so it should be fine for you to do it. Cool. So this was all the initial setup, but now let's go into a bit of the details, saying, hey, second, and just open up the chat window here, just in case any questions that come up. Okay, cool. So first thing that we look into is the variational autoencoder. I'll just download this already. This is actually the one that does the latent space. right? So this is the last topic that I covered, where I said, hey, actually, all of these we looked at as images, but in reality, they're always done with latents. And using an autoencoder, you would first code the image into a latent space, and then everything else happens in the latent space. So this variational autoencoder is the one that does that. So it is the one that allows us to operate in the latent space. Then the next, you have the OpenAI clip encoder. That's again directly downloaded from OpenAI repository itself, because it's available open source, and you can see it's a vision text transformer. So that is the second component. So it's a bit different from the diagram itself, but the diagram tries to oversimplify it a bit. But if you go back to the diagram where we had this, so the one on the left, this is the text encoder. The one in the middle is the unit that we will come to now, and then the one on the right is the image decoder, which is the decoder part of the variational autoencoder. So the one that does it in the latent space. So we have already loaded this, or all of this, basically, it's one model. And then now we loaded this, and then next we will load the unit. So this is the clip tokenizer that we just loaded. Before that was the variational autoencoder. Then the next one is the unit. Again, you can see I'm loading all of this from the same repository. So for example, the unit is from the Stable Diffusion v4 repository. Also, the variational autoencoder is from the same repository, except for the OpenAI clip, which comes from the OpenAI repository. So those are the three components that are loaded. They're all, so you can see that Stable Diffusion is not really one model, but sort of a combination of different models, which is also what makes it so awesome when you go in the direction of applications and so on. Then the next step that you need to do here is the scheduler. We didn't really cover this in too much detail, but when I talked about adding noise in those steps, that noise is added at a certain schedule and in a certain way. I briefly mentioned this, it follows a Gaussian distribution and so on. We're not going to go into too much detail. There are different kinds of schedulers, which basically determine how you split up the noise, or how fast or how soon you denoise the image. So do you add a lot of noise at the beginning and little noise at the end, or do you add noise progressively, which is what we are doing, like a linear schedule? So you just keep adding a bit of noise each time, or you do it exponentially. So it's just a way in which you add noise. It has an impact on how fast or how in a certain style you kind of denoise the image at inference time. For now, I would say just stick with one, or just for the sake of explanation, we will just stick with the linear one. So we just assume that at each step we add a certain bit of noise. That's basically what you're doing. Then you put everything to the GPU. You definitely need to use the GPU. You can use it actually on a CPU. There is a lot of cool models out there that allow you to even run it on a phone and stuff like this. So there's really an amazing amount of research in this direction. But yeah, just as a default, I would always use a GPU. Now we set up the, so we're doing inferencing, right? So we're trying to inference an image, we're trying to generate an image. So you set up the parameters to do that inference, which is, for example, height and width. This is just something I set up. There are some limitations based on the type of model, but again, just going with the defaults. Number of inference steps. This is basically what I meant when I was saying when you do inference, you do multiple loops through the same unit, because you cannot denoise an image completely in just one step. So in this particular case, I'm choosing to do 50 steps. So 50 forward passes through the unit. So you just keep doing on and on. So that's what I chose. Guidance scale, I will come to in just the next cell. And then, yeah, just I need to generate only one image. I don't want to do more. And I also set some kind of manual seed. You can keep changing it. So nothing really crazy over there. Now we actually come to the prompt, right? So this is the prompt that I want to use. A digital illustration of a koala in the Australian jungle, 4K, detailed, trending in ArtStation, warm and sunny colors. That's just the prompt that I chose. Now, when you remember when I said that the first thing that you do is embed this prompt in the OpenAI clip embedding space. So that's the first thing that we're doing here. So you take the text, you say this is text input, you take the prompt and you use the clip tokenizer to first tokenize your prompt, and then you use the encoder to then embed it. So what you get now here as your text embedding is basically the embedding of your prompt in the OpenAI clip embedding space. So that's kind of what we discussed. That's exactly what is happening. The next step is actually the blank text embedding. And this is where it differs a bit from what I explained before. And this is an additional trick or hack, whatever you want to call it, that the authors use to direct the denoising process a bit more towards your prompt than not towards your prompt. So what do? They say, I'm actually going to do 2 forward passes through the unit. In the first case, I'm going to put in the text embedding of the prompt that I want. In the next case, I'm going to put in the blank text embedding. So what if there was no text embedding, then what the model would have done? And that's what happens in this step, where I have basically said blank, my prompt is empty, and I try and do the same thing. I embed it in the clip space with the blank and so on. So I get what they call unconditional embeddings. And now I encode them together. This is just a matter of convenience, but basically now I have 2 OpenAI clip embeddings, one with the prompt, one without the prompt, okay? Keep this in mind as we go to the next step. So I'm just letting it run. And in the next step, we set up the scheduler, we set up the latents. So this is basically random noise. I'm basically saying, please create to me random noise in the shape of X pixels by Y pixels, completely random noise. That's my starting point, right? That's what I also discussed, that it's completely random. And then I just set up some, more like vector things to make sure that you have different copies of it for the different number of inference steps and so on. But now we come to the actual loop that is happening. And this will happen now 50 times because that's the number of steps that we have set up. Then what you do is you put it through the model. So you have the latent model, so the random noise that you created, then put it through the forward pass of the unit itself, and then you get noise, and you get 2 kinds of noise now because you have done 2 forward loops. One is the noise with the text, one is the noise with the unconditional one. And now what they do is they kind of make this noise more than it is in the direction of the text embedding. So basically what you're saying is, if I had the text embedding, I would do this. If I didn't have the text embedding, I would do this. Now, please increase this with this guidance scale. So this is that parameter which we put there as 7.5. You can change the parameter value for this. But what we are saying is, hey, please move this image generation more in the direction of the one with the text embedding, and less in the direction of the blank embedding. So this is an additional hack or kind of way to tune the model to denoise the image more in the direction of the one with the text embedding that you have, and less in the direction of the blank embedding, which anyway you don't really care about. So this is a way, another hack to guide it. So guide the model to denoise it in the direction of the clip embedding of the text prompt that you have given it. So that was one difference between what I explained there and what happens in the code. And the second difference that you can see here is that we are actually predicting the noise, right? So we are actually not predicting an image with less noise, but we are actually predicting the noise. And then you subtract that noise from the original image to get the new image. So it's just a bit of a mathematical thing where you don't predict the entire image itself in a denoised fashion, but rather you predict the noise and then subtract that noise to then get it into to the next image. So you still get the denoised image, but not directly from the model, but you predict the noise and then the noise is subtracted. So that's basically what is happening. And now when you run this, it will now run for 50 times. And at the end, what you get is still a latent representation. So you still have a latent, so that's in this concise latent space that's called as latent. And you still need to go from that latent representation to the image. right? And that is what is happening here, which is basically that you're using the variational autoencoder now to decode it. So that's that last part that we had at the end. So what you've done here, you have taken, you started with latent. So everything is happening in the latent space. You start with random noise. Then you have these two types of text embeddings. You run both of them via the model to predict the noise. Then you amplify the noise in the direction of with the text embedding so that the model is denoised in that direction. And then you run it via 50 times. You finally get a latent representation, and then you decode that latent representation to get the actual image. And then let's see what the image looks like. That's the koala in the Australian jungle, 4K and stuff like that. So that's kind of the image that you got. But imagine that this image is also come from the latent, and the latent is what you then got here and so on. So that's basically the code explanation of each of those components. I didn't really go into the training code itself. This is, of course, also available. You can go deeper. They also provide information on how you can train these models and stuff like that. So really, there's a lot of information here. And there is a lot of information on how you can adapt, condition, and all these models. So there's like a huge space. Maybe we can cover that, maybe not. I will stop here because that kind of covers the important aspects of the paper itself, and also the code aspects and so on. But yeah, it's just now open round for question and answers.
We have a question from Akash pending. Does clip embedding give a joint text and image representation when we only embed the text prompt through it during the training and inferencing? I think you can just read that question. I think quite condensed questions.
Yeah. So I guess just to maybe clarify, the clip model itself is trained separately. And when the clip model was trained, they used a set of, so an image data set, which had images and captions along with that. And so that's how they trained it. Actually, I can just quickly show you. Maybe that helps. Clip model OpenAI blog. They actually explain it quite well on how they do it. The data set itself is not open, unfortunately, so nobody really knows what data set they actually trained on. And when this model actually came out, I actually read the paper and I had no idea how I would use it. And only when I saw the Stable Diffusion model, I was like, oh, okay, that's how you do it. Yeah, but you can see here that they have different kinds of, so this is Pepper the Aussie Pup. That's the caption for this particular image. Then they have a text encoder, which creates this embedding space. And then you have an image encoder that does it for the image from that. And then this embedding model now is trained in a way that the images that are close together are as close together as possible. And they create a fake image data set in a way. So for example, they would take the same image and they would say maybe Pepper, the Indian, I don't know, monkey or something like that. And that's the negative image. So that's called contrastive stuff. So they basically create negative examples, and they try and train the model in a way that these two things would be as far apart, and the ones that should be close together are as close as possible. So you get this embedding space, which is sort of a joint image text embedding. And that is what we use in the Stable Diffusion model. So when you have a prompt, you basically take that prompt and do this. So this is what you get, and find that prompt in this embedding space. And that's what you use when you're training the model and also when you are denoising it. So Stable Diffusion itself does not create any joint image text representation. That comes from Clip. I don't know if that answers the question, but yeah, hopefully.
I think we have the last question from Maheshwaran. Why not denoise in the direction of the text embedding solely? Shouldn't that be more tending towards our desired generation? I think this is related to when you were explaining the whole algorithm around text embedding and basically combining unconditional and conditional one.
Correct. No, it's a really good question. why do we do it? I think is because of what the authors found as a hack, to be honest. So so let me also think about it. I think so I think basically that it's sort of a way to guide the direction a bit more strongly than maybe just kind of using the embedding space itself. At least based on what I have read so far, it kind of seems like that works a bit better because you have something within the embedding space to compare it with, and sort of moving away from the embedding space itself, right? So when you have only one, you just have one point in time. Now I'm really thinking aloud. It's a really good question. I also haven't thought about it. When you have like this embedding space, and you have only one point in that embedding space because it's a clip embedding, as opposed to having 2 points, and you want to sort of move those away, further away from, so you get a sort of directionality, I think. That's kind of how I would reason it to myself. But actually a good question. I'm also happy to look into that. And Chaitanya says something like negative sampling. I guess, do you mean maybe that's the answer to a different question.
Chaitanya, if you want to basically unmute and probably just explain your question, that will be easier.
It's not a question. I just wanted to help out in that question with Maheshwaran. So the similar trick is used in Word2Vec also, where they want to push things which shouldn't be together far away. So I thought maybe that might be helpful. But Siddharth put it much better. So.
No, thanks a lot. I just wasn't sure if it's a question or not, but thanks. I think Sumod also chiming in. Yeah, great. My guess would be you need to use visual features as well. I would guess if you just give text, then purely those particular objects will be added.
Yeah, I can just chime in. Hey, Siddharth. So you are sort of learning, you're learning how objects look like, but also you want to learn other things like smoothing of object boundaries, how does light fall. There are a whole bunch of other phenomena as well you want to learn. So by combining them, you are sort of getting both the best worlds. If that sort of makes sense. That's what I would assume. I haven't tried this, but that's what I would assume. So meaning, if you only gave it always to follow the text direction, you'll end up with bunch of. It will follow some amount of those things because your embeddings have learned those. But to some degree, it will feel as though the smoothness. You will have a bunch of objects all correctly placed, but they all won't have that smoothness, sort of smoothness that you would expect, or lighting of one object will be very different from other, etc. So
damn interesting. I also never thought about these different concepts coming together. Yeah, exactly. I also think it's very interesting your take on it, Sumod, as well.
One more small thing I was going to say this, and I don't know if others know this. So always looks like magic, right? In the sense that why does just randomly multiplying something give you this? And I don't know if any of you know this, but this is very similar to how Google does PageRank. So this might seem completely two very different things, but the idea essentially is that, again, just very, okay, I'll just take 1 minute here, but the idea essentially is that to compute PageRank, so you first get you get all the words that are similar, and you get the inverted indexes. From them you get all those items that are similar, and then what you need to do, you need to give them, you need to rank them, right? So Google's PageRank, the idea was that you take connections between websites, put them into a billion by billion matrix, and now you take eigendecomposition of that matrix. Okay. Now, to find eigendecomposition, you need to do an inversion of a 1 billion by 1 billion matrix. That's very expensive. It's not super expensive, like few seconds maybe, but for each user, if I need to do a few seconds of operation of compute, that's just insane, right? For the amount of traffic they have. So, so now what they figured out, and this again is known, is that something called power method. Okay, the idea of power method is you randomly initialize a vector, and this randomly initialized vector is multiplied by your matrix A. Okay, and if you iterate it, say 10 times or so, okay, so just a vector matrix multiplication, you multiply it 10 or 20 times. By that 20th iteration, your vector, this first vector, the vector that you kept multiplying iteratively by. So essentially what you do is you take the vector, multiply, get the output, again multiply, and keep doing that, okay? And that vector will be in the direction of the principal eigenvector.
Yeah.
Okay. And so that's exact same thing's happening here too. Okay. In the sense that you've got a vector, you're embedding that is the direction which you want to move, or it's a transformation matrix, and you're applying this transformation matrix sort of n number of times. If that makes sense. I'm sorry, I'm not visually showing this, so it might be slightly over the head, but if others are interested, I can show it some other time.
Definitely. No, it's really interesting to see those takes, right? Because yes, exactly. You said somehow it looks like magic, and then are you trying to figure out what the hell is going on here? But that's so kind of like this approximation, like in this iteration kind of way, you don't get the exact answer, but you kind of go in the direction of the answer. Yeah, that's nicely explained, or nice analogy.
Thanks, Sumod, and thanks, Maheshwaran, for that question. I hope it was answered. If not, just feel free to unmute and basically ask sort of clarifying questions. Cool. Sid, we can continue with the session.
Yeah, I mean, I'm kind of, so there is a couple of slides more that we could take in, but I would just maybe cover the last bit that's left. So this is sort of add-on material, and then feel free to chime in. Really enjoying the discussions. That's also the goal of our session here, or any paper discussion is, it's really us trying to learn together. So that's what I really enjoy as well. Cool. So this is a very quick recap of the fixed forward diffusion process, where you go from the data all the way to noise, and then you have the generative reverse denoising process, which is what we have done. So just to kind of summarize the whole thing, we also add some latent stuff in there, and we added the clip stuff in there. So that's basically what we did. We already have the notebook and so on. I now wanted to just briefly talk about adapting these models, because I think that's actually where the whole community and this whole space has exploded. Because this, in fact, what I'm showing here doesn't even cover really the breadth of what is there. So because the Stable Diffusion is so modular, right? So there is a clip model, which is completely different. There is a variational autoencoder that's also completely different. Then there is the UNet and stuff like this. The community kind of already figured out a lot of hacks or ways to do it. So first example is Dreamboot. This is a paper that comes from Google, where you fine-tune Stable Diffusion by retraining on specific images and align that with text tokens in the clip model, right? So what is happening here, and this is those popular apps. I don't know, maybe Amir, did you also use Dreamboot then in your the training as well as the startup also?
Yeah. Use Dreamboot. It was like actually December, January timeframe. But later on, LoRa came in, and LoRa was like much faster. And in Dreamboot, what you do is you have to basically store the whole model. So it was like 4 GBs, but LoRa, you can have, say, 100 MBs sort of adapter, which was much easier to train, better results, easier to store. So
yeah, very cool. Yeah, I thought so, because it was a super fascinating time and space as well. So in Dreamboot, what we do is you already have the clip embedding model, and then you identify tokens in this embedding model that are never used or very rarely used. And you can see some examples of this, like SKS, OLIS. These are actually tokens in the embedding model, which I at least don't know what it stands for. So what people typically do is take a bunch of images. Like this is typically the case where you have selfies of yourself, like 10 or 15 images of these selfies, and you would caption each of these in that particular way. So a dash, a SKS man or a SKS woman, and stuff like that. So you basically use the token to now not mean SKS, but mean Siddharth, for example. And then you are basically fine-tuning Stable Diffusion on these set of images. So you have the image captions, but now these image captions will, use the OpenAI embedding, and then because you're fine-tuning it, it adjusts the weight so that SKS now refers to you. And then you can use this fine-tuned model to say, generate an image of SKS in the desert, generate an image of SKS in the water, or something like that. So it's able to basically understand SKS as a concept, which should stand for your face. And the other concepts still remain the same, which it already knows from the OpenAI clip model, right? So that's kind of, that was the dream booth kind of way. Then there was something called textual inversion, which is sort of the opposite in a way, in that you replace the value of the embedding itself. So you pick a certain, like you don't fine tune the weights, but rather you go and change the value of the embedding itself. This is, I think, not as favorable now, and probably the most recent one, as Amir said, is LoRa, which is also a bit more complicated to explain, but it's also applicable across large language models and so on. So it's not just for Stable Diffusion, but these models are damn huge, so like 175 billion or whatever, and you cannot fine tune it. I mean, if you fine tune it, it's just going to take a long time, and you have to save it again and stuff like this. So what people did was insert matrices in between existing layers. So if you actually look at this paper, let me maybe open up this paper, because it has a pretty nice kind of image for it. Yeah, so you see here, you have, so let's say this is one layer, this is another layer, and you basically introduce a sort of hack in the middle, where you are still, to the model, it appears the same, but you have sort of replaced the multipliers between them. So the way I imagine it, you have these layers stacked together, they're all connected to each other. You go sort of between two layers with your own vector in the middle. And again, you fine tune the weights, or you adjust the weights of only that model or that part in the middle. So you're not changing or tagging anything at all of the rest of the model, but only of this piece that you have inserted in between. That's kind of what they show in this as well. Again, very well used, or very highly leveraged by the Stable Diffusion community, but also now increasingly by the LLM community, and to create multiple versions and stuff like that. So that's just part of it. There is also ControlNet. And in the case of ControlNet, so the whole, I would say this class of image adapters are basically about changing the entire model by changing different components and so on. There is another class of models called as ControlNet, where what they do is that you can actually sketch something, like really scribble something, and give that to your model, give that to Stable Diffusion along with the text description. And this goes in the direction of image to image and sketch to image and stuff like this. And the thing that they modify is basically the connection, this kind of denoising process. That's where they go in and change it, where they say, for example, in our case, we took the text embedding and the unconditional embedding, and we said, please direct it in the direction of this. And in the ControlNet paper, what they do is they say, yeah, there is a text embedding, but also for 50% of the examples, don't use the text embedding, use this sketch that we have provided to guide your direction. So they actually, that's why they're controlling the generation. And that's also what the text process does. But basically, that's the point in which they hook on to the diffusion process. So they don't really adapt or change the diffusion process or the unit as much, but the way they do it is by hacking into the text encoder and kind of saying, okay, for 50% of the examples, follow the text embedding, and for the rest 50%, follow the image embedding, which is the sketch or whatever, so that overall, the model kind of also goes to the text prompt and also goes to the sketch direction. So you can actually just draw a sketch of a house and mountains and then say a beautiful idyllic landscape with, and so on, and it generates that really beautifully. So that's called ControlNet, which is again completely different. So there's really a lot for follow-up, but that was not the intention for today. So I'm just kind of briefly mentioning that more than anything else. Feel free to follow up on that. I also put in the links to the papers and so on. And yeah, if you have ideas, I mean, we can also chat about it. And just as a final note, there is this link called Civit AI. So you can look it up. That's basically a community website with all kinds of models, but advanced warning, there's really a lot of NSFW content there. So don't blame me if something else pops up. It's a really crazy world out there. So be responsible with how you use it and what you do with it, but just wanted to also point you in that direction where people are doing all kinds of custom things and so on. So yeah, I'll probably stop there as that was my last slide. Happy to discuss further, take any questions, but hopefully there is some value that you took from today's half an hour or so.
Thanks, Sid. Thanks for that very informative session. Folks, feel free to ask any questions. And we can actually even have open discussions. Like if somebody wants to just share what they understand about it, we can actually get their thought as
well. And just as a note, I think Bharat will also set up similarly the session for next month, which is Transformers. So yeah, keep a lookout. I think the idea here is to really form a nice community together, learn together, figure out what all these technologies are. And let's keep that community going. Okay. Yeah, seems like no further questions or something. So.
Well, guys, glad everybody enjoyed the session. And thanks Sid again. Thanks Bharat, as well as the Fifth Elephant Group for organizing that. Sure. If anybody wants to hang out for the next 5 minutes, otherwise then we'll close the session.
Hey, thanks a lot, Sid. It was very well structured, so really enjoyed it.
Thank you, and look forward to some of your insights in the coming weeks and months, right? Yeah.
Hopefully.
Sounds great. Okay. Yeah, feel free to reach out to Amir and me. So thanks a lot, Amir, as well for helping and also moderating. Really enjoyed our collaboration as well. And yeah, hopefully we keep this going. And thanks, Bharat, for initiating everything.
Thank you, everyone. And have a wonderful weekend ahead. Thanks.
I'll do that as well, Bharat. I'll post the link on the community site so then everybody has access to it.
Cool.
Thank you.
Have a nice Friday, everyone.
Enjoy.